Okay, so now that I have everything set up, can everyone hear me? Does anyone have any questions about what we did last class? Or does anyone have any questions about anything related to homework or the task before we start today's lecture? Everyone's pretty good with everything in terms of where you feel like you're at? Excellent. And here, and just to confirm, the online group, you can hear me fine? Excellent. Okay. So does everyone recall where we last left off on Thursday?
Thursday is still chapter 7, isn't it?
Well, so we're still covering the basics of objects, but the chapters are going to start bleeding together in terms of the way that the concepts are taught. So that's right. Yeah. So we had gotten to the point where, if I'm not mistaken, let's take a look here. We had defined a account class to model an account for a ATM machine. And so we've identified our instance fields that each individual account should maintain. So we identified a name, which we represented as a string. We identified a PIN passcode, which we identified as a string. We have created an ID number that allows us to identify a particular account instance. And then we also have a balance associated with each account. And so those are the instance fields. And just to illustrate that we can also pair our class with static fields, with class fields, we have a class that represents the total number of counts of accounts. So, and then we use that as the basis to generate our ID number. So where our ID is just what temporal occurrence was this account created in the sequence of created accounts. So the first account would be account 1, and then the second account would be account 2, and the third account would be account 3. The 10,000th account would be 10,000, right? And then after doing that, we slowly implemented each of our methods. So if you recall last class, we started designing our software object. We started designing this account object by using a 3-tiered table. In the first tier, in the first row of it, was the name of the object we wanted to define. And let's go back to that. Was the name of the object we wanted to define. In the second row was the collection of properties that we need to define that represent this particular object. And then we delineate whether this data is public or whether it's private using the arithmetic symbol that we put in front of it. So a minus sign represents private access, and the plus signs represent public access. And then in the third row, at the bottom of this, we represent the set of behaviors or actions that this object supports. And that's effectively the API into our object. This is the actions we can cause our object to do. And we said that objects, one of the powerful things about instances and using classes is that we can construct an instance. It's a process that we call instantiation. So when we instantiate a class, it means we construct an instance, and the one role of the constructor is to go ahead and define values to all the instance variables, to all the instance fields. So that's why when we started defining our class here in terms of Java, we declare all of the instance fields, but they aren't assigned a value until the constructor is defined. So the role of the constructor is to set values to all of the instance fields, just like so. And so here, sometimes you know what the default value would be. If that's the case, you just set it. Sometimes you don't know what the default value is going to be. It needs to be passed into the constructor as a parameter. All right, so does everyone feel confident and comfortable with those concepts? Then, since these are all private, they're neither readable or writable from code outside of this class. So in order for these values to be read from external classes, we will create query methods or getter methods. Getter methods are public so that they can be called on from client code from other classes. And what the getter typically does is just return back the value that's held inside that instance field. So here we can get the name, we can get the ID, we can get the balance. And so that allows us to get reading access. Now, we still don't have writing access, and the idea behind why we don't have writing access is that we are using typically fundamental data types, the foundational data types, to represent the characteristics of our object, right? So like, for instance, when we say an account has to have a name field, well, that has to be represented as either text, either another object or text or a number or as a Boolean, right? Those are our like kind of four options. I guess you could throw a fifth option as a collection of things as well. So typically there's like 5 different types of things something can be, either a reference to another object, either a collection of something, or one of the foundational data types. So text, number, or true, false, Boolean value. But because of that, the foundational data types, these very fundamental data types, can very often have a larger set of values than what you are using to model that particular behavior. And I'll give you an instance for that. This is where we're really starting to motivate on why we don't want to give direct access to our fields. We want to ensure that the state, recall state refers to the set of values inside of our instance fields. We want to make sure that the state of all of our objects are always valid. And sometimes you can have a legal value for, say, for instance, an integer, but it's not valid for the way we're using it to define one of our properties, right? And so here, what we were about to get into was implementing, let's see, so we implemented get name, get ID, get balance, equals pen, and toString, right? And so what we were going to do was we were going to implement withdraw and deposit. Does everyone remember that? It talked about being able to withdraw and deposit, because that's where we're actually starting to get to interesting things with this account object. And in addition to implementing our account object, we just don't do that in isolation. We also built a tester class. So as we implemented our methods, so the first thing we did was we stubbed out all the methods. Stubbing out means we declare them, but we ignore giving each of the methods a well-defined body. We create an empty scope of code. We just open and close our brackets. And then if it needs to return something, we return a dummy value. So if it returns a Boolean value, we just like return false. If it returns a numerical value, we just say return 0. If it returns a string value, we just do null or an empty string. And the idea is that we will step through and we will implement a method at a time and then test to make sure as we implement, our methods are doing, they're behaving, our object works the way we expect it to. By creating these, by creating client code that interacts with them in the way that we would expect to interact with it in the real application. And so the motivating goal here is by the time we're done designing our method, we can hand it off to the lead software developer. They can integrate your class into the software system that everyone's building out to, and you can feel guaranteed that the work that you've contributed won't break the system, that it'll work seamlessly as it gets deployed and intermingled with the rest of the code base, right? So that's one of the powerful ideas about object-oriented programming, is it allows us to start defining our code into these very modular, discrete components, so that we each can assign, like if I were the lead developer, I could assign a part of the code base to each person in this class. You can work on it independently without having to get code from your neighbor, and then I could bring it all together assemble it and have something that actually works, right? So the fact that we can work on code concurrently is a very powerful concept driven by object-oriented design principles. Whereas previously, the techniques we would have used wouldn't work well when you have more than one person working in the same code base, right? Does that much make sense? Can you explain what this means and how it's been used? So that's a great question. Recall, up until we started talking about instance fields, there's effectively 3 different scopes that variables can live in. So variables can live inside of a method scope, or what we'll call local scope. And so oftentimes you can even nest a variable into an even deeper scope than that. Anytime you have a set of curly braces inside of a method, that variable is going to be scoped at that level as well. But very broadly speaking, it exists inside of the method level. When that method is done executing its actions, that variable falls out of scope and it's discarded. It's garbage collected thereafter, after that method's done doing its work. And so sometimes if you need to transfer some computational work from one method to the other, you have the return keyword to allow for that to happen. That way you can have one locally scoped variable sent to another locally scoped source so it can be used. After we learned about local variables, because that's where we started from, we then learned about class variables. Class variables are scoped to the class itself. One giant limitation of class variables is that they can only have one value for the entirety of the class. So once it's set, it has that value throughout the life for everything else inside of that application. So when that application refers to that class variable, it's going to be the same value all across the application, which sometimes is the behavior you want. But for the instance of starting to design accounts where you want multiple instances of a similar thing, then you don't want a static variable. You don't want a class variable. You want an instance variable. Instance variables allows us to produce instances of a class, any number of instances of a class. And so we have to use a different keyword to access the value of a particular instance. So the keyword we would use to access the class variable was the class name itself, right? So when I needed to access, and let's go back to account here. So inside of account, whenever I go to access this static variable called count, notice I use the class name account, and then I use the dot operator. The dot operator implies that the thing on the right-hand side of the dot is inside the thing on the left-hand side. So there is a count field inside of the class account. Now, if I want to access these instance variables, these aren't defined at the class scope themselves. They're only created when the constructor is invoked. So when you build an instance, when you use the new keyword, invoke the constructor returns back an instance of that class that you can then store in the variable of data type, whatever that class name is. So if my class name is account, then I get back an account instance. Now, since I can have more than one account instance, I could have 1 million account instances, the special keyword we use inside of account to reference this particular instance's value is the this keyword. So the this keyword is used inside of a class so that each instance can distinguish from other instances. So again, the reason why we're using this keyword is I have 2 variables on line 9. There are actually 2 different types of variables. The one on the right-hand side of this assignment operator called name is the local variable that's declared inside of the parameter list. Notice I have my parameter list for my constructor here. I have string name right there. That is a local declaration of that variable. When I say just name here, I'm referencing the name that is inside of the parameter list. Then on the left-hand side of this assignment operator, I have a reference to another variable that's also called name. So I don't want to access the local variable. I want to use the local variable name to set the instance field inside the class. And since they share the same name, I need to use a fully qualified path of where this variable exists at. And doesn't exist in the class scope, it exists in the instance scope. So I can access the instance scope using the this keyword. That's what the this does. It's a special kind of pointer. It's a special label that each instance has access to that's different than all the others. So for instance, if I create it, let's go over here into the tester. When I create this account here, where the name is Joey, and we go into Joey getting passed here, well, the instance field for account 1 is going to then reference Joey. So this dot name inside of account 1 is Joey, whereas when I go to create this additional alternate account instance where the name is Susie, and I pass Susie into the constructor, then what's happening here is Susie is this value in the parameter list. So this dot name for the account 2 instance references Susie in memory. So even though they both say this dot name, because they exist in 2 different instances, they are going to refer to 2 separate sets of values. Hence the word this. This is very specific to each individual instance. So this dot name can have, if we have a million different account instances, then it can have in a million different sets of values, each one self-referential into itself. Does that help explain that, Philip? Excellent. Does anyone else have questions related to that? That's can be one of the trickier things to conceptualize, is what we're actually doing with this. And the important thing to remember is just recalling that each time we call the constructor, it's generating a new account instance in this case, and each one has its own name, and it has its own PIN number, and it has its own balance, and it has its own, let's see, what was the other thing? PIN name and its own ID number. And we even tested that, right? Isn't that something we tested when we were testing new? So recall, in the tester method, we actually implemented some of these out. So in this tester method, the first thing we did was we create a Boolean value just to say our test defaults to a false state. And then we start performing our test. So for instance, here we created 2 different account instances that we are going to call account 1 and account 2. Then I create my expected behavior that I should get back. And so I'm going to use that toString method to be able to represent the state of my object as text, as a string, so that I can use it for evaluating, for comparing, for testability. And then here, I'm going to set test pass if my expected value, which is this string name, Joey, account ID 1, balance 0, is equal to the toString method output that I get from account 1. And then I'm also going to compare account 2 to the expected account 2. And in order for me to get a pass value inside of my tester method here, I have to pass both those tests. And then if you recall, I was running these. So let's clear this and let's see where we last left off. So and we see that I passed being able to create a new instance. I passed being able to go ahead and test my PIN number, which was to compare a PIN number to a prior to the internal PIN number, right? Everything else we returned back, but we decided PIN numbers shouldn't be easily accessible, that we can pass in an attempt and it lets us know whether we got it right or wrong. We were able to even test depositing the value, right? And I think that's where we last left off. And we were starting to talk about, well, what are potentially some of the risks, the exceptional behaviors that can happen. So we start to motivate why we want our instance variables to be private. It's because they represent a particular state. Our public methods allow us to control how that state changes. So the only way that the state changes over the course of the application life cycle is when they're called to do so by methods that we control and define. So, and then we were starting to talk about, let's see here. Yeah, so I think this is where we last left off. And so I know we had gotten some suggestion when we go to implement our withdraw and our deposit. So I think this is what we started with, right? And we're like, this seems to kind of work, right? I have a deposit. I can pass in some amount, and then whatever the balance is when I deposit, I'm adding to it, right? The idea of depositing is I add to whatever the deposit amount is to my original balance. So if my balance is zero and I deposit $100, then I should now have $100. If I then deposit $50, I should then have $150, right? So my balance each time I deposit more money should incrementally keep increasing. And for withdrawing, whatever this amount that gets passed into our method, it should reduce our balance. So if I withdraw $50, and if I originally had $200, then I should now have $150. And then if I withdraw $100, then I should then have a $50 balance. So my balance will constantly decrease each time I withdraw money from it, right? So the question then becomes, is this a suitable implementation to ensure that our account object will always have valid states? So what is a valid state for, let's start talking about this. Like, what's the valid state for a name, for instance? So yeah, so it probably an invalid. So let's identify an invalid state. So what might be an invalid state then? A number, or maybe just something that's blank, right? So it could be a number, it could be something that's blank. Let's do the blank thing because that's a little bit easier to check. So when we go and we set the number, for instance, or for the name, instead of just blindly setting this, perhaps I should be checking to see if it is has an actual value inside of it and isn't an empty string, because maybe that's what we would consider an invalid name. Now, I'm going to kind of, so these are the things we want to try to plan for while we're implementing and planning out our steps. I'm going to ignore the name component, although we should protect against that, because I want to focus more on the other thing that we're really considering is balance. So what we're about to do, what we're about to talk about would extend to name, but I don't think I want to spend the time to actually, well, maybe, we'll see. We'll circle back and we'll correct name. But let's talk about balance. What is a valid or invalid state for balance? Numbers, right? Should it be any number? Positive numbers, right? Like your account, you shouldn't be allowed to have a negative account, right? That for an ATM, it should only be zero. Zero should be the bottom line, right? You start at a zero balance. You should be able to deposit money into it, but it should never be negative, like, because that will go into an invalid state in terms of the amount of money you have, right? You can have zero money, but you shouldn't have negative money, right? So what we're starting to do here is consider the exceptional cases for deposit and withdrawal logic. So what values are technically legal, but should not be valid, as it could lead to broken behavior? Because suppose, what about with our withdrawal method? When we withdraw here, let's jump to deposit. Let me change the order of these so I stop doing that. Okay, so for deposit, for instance, what is the restriction on an amount? Should an amount be allowed to be a negative number? What happens if it is a negative number? Yeah, then I'm even though I'm depositing money, if I deposit a negative value of money, then I'm actually reducing the amount. That's the opposite effect of what a deposit should do. What if I try to deposit a negative amount and withdraw? Exactly. That's like a deposit of money. Wouldn't that be broken in the ATM machine if I withdrew negative money and it just added money to my account? That's probably not behavior you want, right? That breaks the concept. So even though fundamentally, this logic seems to work, it only works under certain constraints. And the constraint is that amount has to be 0 or positive. Because if it's not, if it's negative, then it allows us to do something like this: have a balance that starts at 100, we deposit a negative amount, and all of a sudden we have a balance of 50. We want to prevent that. Let's talk about withdrawal. Withdrawal is even more interesting because with withdrawal, our amount not only has to be positive, but it also has to be less than or equal to your balance. Because otherwise your balance falls into a negative value, and that should be an invalid state for us. So for instance, an example of this is, suppose we have a starting balance of 100 and we attempt to withdraw -50. So that's a violation that creates an exceptional instance, because then my balance, even though I'm doing withdrawal, actually increases. It goes up to 150. And then suppose that I go ahead and try to withdraw 200. Well, my balance is only 150 and I'm trying to withdraw more than I actually have. So then my balance would go into -$50. So notice there are sets of values that can be passed inside both deposit and withdrawal that are legal, but it produces an invalid state in our instance. And so that's what we try to identify when we're creating our methods. What are instances that client code can go ahead and attempt to pass into here that can cause our object to break, that can cause our instances to fall out of a valid state. And then we have to protect against that. So what are ways we might protect against that? So again, the goal of our instance methods, the reason why we make these public, is it allows us to consider these situations, and then we can prevent these invalid states to occur. So our first approach might be to check those values for exceptional cases and just ignore them, right? So let's look at deposit here. Suppose what I'll do is I'll say, if the amount that's being passed in is less than 0, then just return. Stop doing any processing and just return this method back to the client code. And if it is not an invalid, if it isn't one of these exceptional cases, right, then it means that the amount is a legal value and a valid value. And so then we would go ahead and apply our logic, right? So does anyone have a perception of why this isn't the best way to go ahead and prevent client code from setting a deposit in a negative amount? What might be an issue by just ignoring actions that would lead to an invalid state?
People would repeatedly try it.
Exactly. Yeah. In fact, I give a clue right at the bottom of the slide. However, this is a bad design because it doesn't report to the client code why it didn't work. It fails silently, and the code would appear to behave normally because it didn't error out. It didn't cause any issues while you were compiling. So you would have done a deposit, you would have passed in a negative amount, and it would have looked like it did something. And so what that can cause is unexpected behavior, because now the client thinks they've successfully done something with your object. And even though you protected against the change to invalid state, you didn't report that the client tried to do something bad. So the more appropriate, the better designed thing to do is you check values for these exceptional cases inside of your methods, and you throw an exception object an exception instance to the client code, and you let them know that they violated one of the concepts that drives your data model. So here, there's a special keyword in Java called throw. Throw returns back. It's a special way of returning back control to an invoking method, to another invoking block of code, but it only returns one type of thing. So whereas a return statement has an entire clause inside of the method that is the return type, the throw keyword only returns back exceptions and errors. So it's a way of returning back control with information that's relevant as to why this method failed to do what it's supposed to do. And the entire point of a throw is to be able to report to the client code what it had violated. And you've been the recipient, I'm sure, to lots of throws from the command line, right? I'm sure everyone's seen that stack of information at the command line that says, hey, I couldn't do that because I couldn't find this symbol, or there's no index at that inside that array, or the input you're trying to give to the scanner object is mismatch type. Like, these are all examples that it's giving you back information as to why your code didn't work. It doesn't just silently fail. So we can start implementing that inside of our own code base. So in this example, we can throw a new illegal argument exception. An illegal argument exception represents, so these exceptions, as you can see, are very verbose in their naming. So in this instance, it means that the argument that was passed into this method is illegal in this model that we're using it. So even though it's technically a valid value, it is illegal in the way that we want to process on top of it. And then inside of, so notice this is a constructor, we're using a new keyword, and then we're creating a new instance of this. These exception objects have one parameter in the constructor. It's a string that is the message that gets passed to the client code. So this would say that the deposit amount has to be greater than or equal to 0 to alert the other developer, whoever's trying to use your code, why you refuse to go ahead and do this deposit. So does this much make sense to everybody? Okay, so let's actually test this out a little bit. Okay, so right now, and again, we can test the violation. We kind of saw the slides for that. Let's go here into our deposit then and try to, well, first let's implement this. So here we're going to check for that invalid state. So if the amount is less than 0, then I want to throw a new illegal argument exception. And inside of here, I will leave the message that amount has to be greater than or equal to 0. Okay, let's try to test this out now. So I'm going to go over here. Yeah, I mean, yeah, so it's possible probably that you could do probably even a penny, right? So, but it's technically not invalid, even if like our very baseline is technically we can withdraw $0. It doesn't do anything, but it ends up being that edge case. But I mean, that's a really good point. When we're defining what is valid and not valid, it's trying to find where that boundary point is. And so maybe we don't want 0 to be included in that, because maybe that actually leads to really erroneous behavior. Suppose that we do limit it to 1 penny. That would even prevent being able to deposit or withdraw fractions of pennies. However, maybe you want to be able to deposit or withdraw fractions of pennies. I don't know. I guess it depends on the application, but probably in the case of ATM, you don't want to be able to do that because that could probably lead to really weird behavior. So yeah, in this instance, maybe we want our base case to be 0.01. So you have to at least withdraw or deposit a penny at a time. Okay, let's go to our actual tester now. So let's suppose that our tester is here for testing deposits. So let's go to account 1. And let's try to deposit now a negative amount. So let's try to deposit negative $20. So notice it's valid, right? I produces code that allows me to compile. Let's see what happens when we go and try to run that. And so because I've passed in a negative value here at line 46, and I'm checking for this case where if the amount is less than 0, and again, if I really wanted, I could, check whatever this is. So less than a penny, then I will throw this new illegal argument exceptions. Notice what happens with those illegal argument exceptions is the same thing you've seen in the past. If we don't try to catch an exception object, it causes our code to fail, right? We've seen this. But when it fails, it gives me the message. Let me stretch this out some. So here, the java.lang.illegalArgumentException is amount has to be greater than or equal to a penny. And just for the purposes of the slide, so since, yeah, perfect. And then what you're seeing here is the stack of invocations that led up to this exception being, for this exception to actually occur. So if I traced it, if I did this is what's called a stack trace, by the way. If I traced the set of methods, at the bottom is the main method, right? That's the first method that got put onto the activation stack. And then from the main method was the test deposit method. And that method itself called on account to do a deposit. And that happened on line 38. So each time I see the number after the colon, that's the line number that's being executed. So again, if I go to line 8, that is where here we go, an account tester. Line 8 is where the main method was being called, and at what point in the main method it stopped at the instruction pointer. And then inside of test deposit in line 46, so if I go to line 46 here, I see this is the method inside of test deposit that led to the exception occurring. And then if I go, and so here I'm passing the negative value, right, negative 20. And then here inside of account, inside of deposit on line 38, so let's go here to line 38, is where I get that exception object that's actually thrown to me. And then the actual exception object is this one at the very top. So if you've seen these and you haven't quite yet learned how to parse and read through it, that's the step-by-step process to kind of analyze a stack trace. And now we can cause those ourselves. We can cause that to ensure that if client code tries to violate our data model by passing in a value that would result in a illegal or invalid state, then we can defend against that. Okay, so if I want my tester to actually work, though, what I can do is I can wrap this in a try. So instead of just allowing it to fail, because now when I test this, I can't actually test anything else. My tester crashes. So I could put this in a try so that I can catch that illegal argument exception. And let's just call that E. And then here, let me get a string that is a expected. And what number? Expected 3, for instance. And we'll set it to an empty string initially. And then inside the catch, we'll take and get expected 3 here to be set to E dot get message. And then we'll, on our tester pass, we will check to see if the, oh yeah, actually, this should be, whoops, this should be exception. Okay, so that'll be an exception. And then here, let's create our expected 3 as, and then what was our message? Let's go and grab our message. The message should be this one right here. And just so that this is in parallel with the slides, I'll change this back. Yeah, here. Whoops. And then here, what we can do is we can test that our exception equals our expected 3. Excellent. Okay, so let's see what's happening here. I have an exception that I'm going to declare right here so that I have access to it outside of the try catch block. I'm going to try to do this with a valid that I know should throw an exception. Now, the powerful thing about using a try catch block is I can then try to catch the reception, the exception, and do something with it. So I'm going to try to catch an illegal argument exception because that's what I expect to be thrown. I'm going to label it as E. So I'm declaring a variable called E of that data type, of that exception data type. One of the methods inside of exception, and we can double check this by looking at the API, is get message. Let's do that right now. So let's go to illegal argument exception API Java. Let's do Java 18. So we can see that illegal argument exception is inside the java.lang package, which is why we don't have to import it. But there are exceptions that exist outside of the java.lang package. Like, for instance, exceptions related to the scanner object would be inside java.util, in this case I would have to import those. So inside of here, we can see the methods that are available to us. Let's go to get message. So the get message returns back a string, and this returns the detail message string of this particular throwable. So again, at any time, if you want to see what you can do with an object inside of Java, look at the API. It has the collection of all the methods that you as a client code have access to. So I'm going to get that message. I'm going to store it inside of the variable that I've declared on line 46 here. And now that I have that, I expect that the message I'm going to get from the exception will be amount should be greater than or equal to, oh, let me change this back. So let me make sure that this, yeah. So I'm going to make sure that this is the same thing. And then what I'm going to do is I'm then going to, oh, I can't do that though. What I need to do is the dot equals, right? we need to do a dot equals on a string and the expected. So we'll take the exception here. String exception, string, oh, and let me do this. Let's do expected. We'll test with exception. Okay, perfect. And this is going to result in something that's either true or false. And so if it's true, I'm going to add that in as part of this compound assignment operator as one of the additional checks. And if it's false, then I'm going to report that it didn't work. So let's test this out. Okay, let's see. Expectation. Probably want to spell that correctly. Okay. Okay, so we will then take exception. Let's see here. Exception. I guess what I could do is give it a default value. Okay, perfect. Let's clear this and let us run our account tester and see what happens when we run this. So notice I am now getting a true value here. And let's actually change this. Let's change this to say, like, we'll change the symbol here just to make sure that this is working the way we expect it to. So recompile, recompile. And we will run, and now it's going to say false. Yeah, so we're actually testing this exception and getting back this exception object, which is great. That's exactly what we want. So notice we can even, inside of our tester, test very verbose exception handling inside of our classes. So we not only test to make sure the methods work in a appropriate way, in a way that we expect it to work, but we can also test and validate and verify that when a client code tries to provide a value that causes an exception to occur, we can test against that too. That way we do full coverage on all of our methods. So both successful and failed attempts are illustrated. Does this make sense? This is what's called defensive design or defensive programming, where we try to see how client code could potentially break our code and we protect and defend against it. It makes for a more robust implementations. Okay, so now that we have this implemented, let's do the same thing with our withdrawal method. So going into withdraw, here, what are values that lead to exceptional cases with withdrawal? Do you remember what they were? So if we try for an amount to be less than 0 is one instance that we would state is an invalid and illegal value for that argument. What's another? And here, let me create. Is there another one? That's right. Or if the amount is greater than this balance. Well, that's going to be handled for us automatically by the parameter that's being declared. Oh, okay. See, so that's going to lead to a syntactical error because it's going to be a mismatched data type. So you won't even be able to compile your code if you try to do a string. Exceptions allow us to catch these runtime behaviors that are technically syntactically correct, but it produces behaviors that break our conceptual model of an account. And those are much harder to catch if we don't use these strategies to protect against this. So there's a reason why we think so deeply when we start constructing our models in terms of not only identifying what fields they should have, but what fields they should have as valid sets of values. And then when we go and change the state with these methods, we want to protect against it so that we can maintain the integrity of these concept models. Because again, since you're allowed to technically have negative numbers, those are harder to catch. And if you don't catch them, you get an application that looks like it's running, but then it goes into unexpected consequences when your mental model and your actual implemented model fall out of alignment. So we have to strive that we're very precise with the values that get saved or stored into our instances. And we can do that. Like, we have the tools to do that, and we should get comfortable doing that because it's going to make your code much, much better in the long run. Okay, so we're guaranteed to get a double value here. And then what we know we don't want this to be, that's technically it's a valid value, but it's illegal for how we want to use amounts, is we're going to check the invalid states, the states that lead to an illegal argument. And so that's if the amount is less than 0, or if the amount is greater than the balance. So on either of these instances, this is when we want to throw back a new exception. And if we don't throw the exception, then the idea is that the amount that was passed in was valid. It works with, it's congruent with what we'd expect. So throw new illegal argument exception. And here I will go ahead and pass in amount has to be greater than or equal to 0, and the amount has to be less than balance. So here I can check for both these conditions and just make one statement. Alternatively, I could have checked for each individual condition and made a very specific message for each one. So what I mean by that is I could cut this, and I could have just as equally, well, let me not cut that. Let me copy it. I could have checked for this one and then just done the message amount has to be greater than or equal to 0. Then I could have done another one that said that checked the other condition, and then I could have done a different message. But I'm not going to do that. I'm going to do the one check, keep it cleaner so it's not a lot of if checks. And now let's actually test this now. So let's go into our withdrawal. And what I'm going to do here is big violation. Well, no, I won't do that. We'll do this by just actually implementing it out. Okay, so tester pass will default to false. And so instead of returning false here, we're going to return the value of tester pass. Okay, so the next thing we're going to do is we're going to create an account. One, and here we will create a new account. And so here I will pass in the same thing. Let's do Joey. Will be the name, and the pin for Joey, let's just do 1, 2, 3, 4. Doesn't matter. Okay, then once we have that, in order to test withdrawal, I have to deposit first, right? Because I need to have a certain amount. I mean, I could get the exception. I could try to withdraw from a 0 balance, but I wanted to, usually when I want to test valid states first, and then I go into testing the exceptional cases. So let's do standard testing just to make sure that we can withdraw. So before we withdraw, we have to deposit. So let's do, and that's why we tested deposit first. We want to make sure that now that we verified that deposit works the way expected to, we will now use it to build withdrawal. So here I'm going to deposit, let's say 100, which will then allow me to withdraw 50. Let's create an expected value, or double. So our expected value is now going to be 50, right? So now what we can do is we can say tester pass is going to be assigned account1.getBalance is equal to the expected value that we just did right there, right? And so Okay, so let's also test trying to go ahead and let's try some of these exceptions now. So let's try this exception where we will have our exception. And then we will have our expected to value. And let's go and get the message we're going to pass. So this is the message. I'm going to copy that string and I'm going to put this here. So I'm going to have expected to is going to be the amount should be greater than or equal to 0 and amount is less than balance. So here I'm going to, on account 1, attempt to withdraw a negative amount, which we know should lead to an exception being thrown. So let's try to catch the exception, and the exception in particular will be a illegal argument exception, and I'll just give it the label E. So I can access it inside of my my code block here. And what I'll do is I will then save to my exception string the message that's there. And then I will test, I will go ahead and on my tester pass, I will do this compound assignment. So I'm going to compare and add to the tester passer the evaluation of, let's see, my expected to equals and this exception. And then I want to do the same thing because there's two different conditions that can lead to this. So I'm going to do another try catch block where I'm going to do account 1 dot withdraw, and I'm going to pass in an amount that's too large, right? Like 200, for instance. That should fail because that's trying to withdraw a larger amount than what my balance currently has. I'll make it 2,000 just to make, let's just make it a really big number. Okay. And then here, what we'll do is we will catch this, and then a illegal argument exception. I will just call it E. And then inside of the exception, I will set it to be E.getMessage, which will be the same message as before, but I want to make sure that I receive it on these two different conditions. And then I need an expected value here. So let me actually create string expected 3 is going to be the same one here. And here we will then check on our tester pass to see if our expected 3 equals the exception that I get there now. Excellent. Okay, so let's clear this. Let's see if I have everything that's authored properly. I was able to compile, and now let's run our account tester. Oops. And now you could see all of the tests that I want to run and evaluate on my class are now successful. So now I feel pretty confident that I've fully developed, we fully modeled from ideation until delivery an account object, right? We thought deeply about the name. We thought deeply about the properties over this lecture and the last lecture. We thought deeply about the methods. Then we evaluated, and it's not just that we thought deeply and implemented them. We used a test-driven approach to do that. So as we implemented out our object, we built another class with the explicit purpose of testing it to ensure that each of our methods works the way we expect it to. And then we can evaluate the state so that we get valid states and invalid states, and we defend against that. So does anyone have any questions? So like when you start designing your objects, this is the same approach I want you to take. I want you to test step by step while you implement. I will say it's a little bit more work, but it's worth the time investment to do that, because it beats what you always constantly should strive to do is avoid getting in a situation where you're spending your time debugging. It's better to build stronger testing tools now, because what it does is it makes you think very deeply while you're still in the mindset of modeling out this problem. And it's going to save you a lot of headaches later on when you're trying to use these and you realize that you hadn't thought so deeply that it doesn't cause it to start breaking down inside the system. And it's so much harder to fix something once it's been added to the system as opposed to when you're initially building it out. Excellent. Does anyone have any questions related to this?
What does the throw mean?
So the throw is a special keyword inside of Java that works kind of the way that a return works. So recall that a return sends back control to the method, the block that invoked it. So it gives back control to wherever that code was called, but it gives back a value. And the value that it gives back is whatever the return type is. So if the return type is void, it just gives back control. If the return type is Boolean, in this instance, it gives back a Boolean value. If the return type was string, it gives back a string value. Throw returns back, but it only returns back a very special type of value, and that is an exception or an error, something that's called a throwable object. And the only thing that can be a throwable object are errors and exceptions. So it's a way for us to give back control to client code without having to explicitly say that this gives back a value. It gives back a special value, which is an exception value. And so it allows us to let client code know that they cause our code to break in some meaningful way. So the reason why we want to throw that exception, so you only want to throw an exception if what has happened inside your logic caused the breakdown. And we have identified breakdowns in our logic when the amount is at certain values. Like if an amount is a negative value, then it breaks the concept of what deposit and withdrawal are. Or if, in the case of withdrawal, if amount is greater than balance, then it breaks down the concept of withdrawing, right? You shouldn't be able to withdraw more money than you have, right? That doesn't make sense. You shouldn't be able to withdraw a negative amount of dollars. That doesn't make sense. Both those are technically legal values. So your code will compile if someone does supply a negative value or a value larger than the balance. So you can't depend on compilation errors to identify that. That only is going to occur during the runtime process of your application. So what we do is we check for those situations that cause a breakdown, and then we throw an exception. So that prevents the code from running the way that they expect it to, and they're going to get an error message. Or they can try to do that. They're either going to get an error message and they'll be alerted that they tried to do something that caused your code to break, or they can try to do that call in a try block. And so if they do get the exception, they can catch it and handle it. So does that answer your question in terms of what throw does? So throw is always paired with an exception. That's how we send an exception to somewhere else in the code. And in particular, to the client code that invoked this particular method. Now we've been the recipients, we've been the clients to exceptions before. I'm sure everyone has been up to this point with the amount of coding you've done. But now what we're starting to do is learn how to throw them to other client code. So we're learning how to finally implement those exceptions. Excellent. Is there any other questions? Does everyone feel, is this like on par? Does this feel like a good concept in terms of how we're doing this? So one thing I want you to do then is, we have about 7 minutes. Let's try to do a different type of model. Let's try to build out a model, and then we'll spend Thursday implementing that. So I'm going to repeat this process that we just did with an account with a different type of object, but I'm going to try to get you to be a little bit more hands-on with the implementation of it. So we're going to do something, I think, a little simpler than account. Let's jump over here and suppose that we want to model the concept of time. So let's start by building out our table that has the 3 tiers. What should be, okay, so with time, the first thing we're going to do is give this object a name that we're modeling. What's a good name for something that models time? Yeah, perfect. Okay, now we move on to the second frame, right? So the first row, we've given it a name. The second, we will now identify the properties that define time.
How defined do you want time to be?
Well, it's not yeah, I mean, this is a group exercise. So we get to, that's the powerful thing about object-oriented programming. You get to decide the specifications, and you decide those specifications based off of what the application is. But suppose, for reference, we'll model time the same way we model time in the real world, with a device like what's on your wrist or on your wrist here, right? I like this one more because this is more classical. It's analog, it's mechanical, right? So it has one dedicated purpose. We typically have one in the classrooms too, but I don't see one in this classroom. So let's look at this wristwatch, and that models time. That is a analog device, a physical device that actually allows us to be able to track what time it is today. So what properties does that watch have if we want to create a digital, we want to create an object-based representation of that?
That models minutes, seconds, and hours.
Minutes, seconds, hours. So it tracks whatever so there's a concept that drives time then that says we are in a given hour of the day, we are in a given minute of the day, and we're in a given second of a day. So does everyone agree that this is a well-defined representation for time?
Well, I'm sure getting more hours they take after a certain time of the day.
Oh yeah, so you could potentially track the day. So let's say that that's could be a special watch that, and we'll build that watch. We're going to lead that. We'll slowly get to the point where we will build a watch that tracks both the time of the day and then the date as well. So is it a Monday or is it September? Or so there are more feature-rich watches that can do that. But I would say if we want to model that kind of functionality, we probably want to break it down into modeling just the time and then modeling just the date, and then bringing those together into a special watch that's called like a date watch or date time or something that has both the time and the date. And we will get to that point. I really like that idea. So that's what we're going to do between the remaining portion of this lecture and next lecture. So let's focus in on time then. The first thing I'm going to do is I'm always going to define my instance fields to be private. So everyone know or recall what the motivating principle behind that is. Exactly. So that no other class has direct access. And the reason why is that we want to make sure that our methods are the only thing that sets state. And we should understand why that's so important, because the account class, there was data that could cause our fields, our properties to become invalid, and it would break down the logic of what we're trying to model. And the same is probably going to be true with this as well. So we're going to set these to private, and this is universally so. You should always do this, because if there is a breakdown in your objects, you want to know that the breakdown is happening in the object itself. The objects are responsible for maintaining their own state. Okay, now let's talk about how we might model these, the underlying data that we are modeling this. What is the underlying data that we might use to model a minute? Yep, that sounds perfect to me. An integer. What about seconds? Yep, and what about hours? Perfect. Okay, so now we have defined our set of fields here. Now let's define what methods, what behaviors we might expect for our time to have. So suppose that we have a constructor. And so with our constructor, we probably want to be able to pass in the hour, the minute, and the second. And here we'll also identify what those should be. So they'll be integers. And then let's see here, suppose that we have our toString method that's going to return back a string representation. This way we'll be able to test our time class as we design it to make sure that as we set it, as we change state of it, we can inspect it and verify that what's happening with our instances is incongruent with our plans or concepts for it. And let's also have two different types. So we'll have a toString that just represents the base time. And let's say we have one that represents it in like a inside of like a AM PM. Which will also be string. So here, this will just represent the state as whatever the numbers are. This will actually do the DST, whether it's, well, maybe not daylight savings time, but allow us to say it's like 3 p.m. as opposed to, say, for instance, $1,500. So there are two different formats that we can report our time in. So suppose that these are the methods that we have. And then there might be some helper methods that we want to set up. Like, say, for instance, that let's say in this particular case, when we define our time, we don't ever want it to change. So once it's set, it becomes immutable. But suppose that we have these helper things inside that we're going to do, like maybe a set hour, a set minute, and say a set second. And so those will be responsible for checking each one of those states. So this will take in a hour that represents an integer, and that's where we will check to make sure that that is valid before setting it. Again, we'll do this as a minute. So let's take minute, and actually we'll make these. We'll make these public. No reason not to. This will be an integer. And then set second will be a integer as well. Okay, so this will be the full. So what I have now is a full listing of the new class we're going to build tomorrow. We have a name, we have the fields and how they're going to be modeled and what the access level is. We have at the bottom row the set of methods we're going to have, their access level, and the parameters that get passed in and what it returns back out. What I want you to think of between now and Thursday is what are the constraints on set hour, what are the constraints on set minutes, and what are the constraints on set seconds that would lead to both valid states and invalid states. What are the exceptional cases so that when we go and implement this out, we can look for those exceptional cases and throw those exceptions with the message. So think about that, and that's where I'll start back up next class.